Now how does this look? So let EI be this I cell. We use the fact that these relative homotopy groups are 0 to say that there is a homotopy, well, there's a null homotopy of this. So we can homotop EI to an I cell which is entirely in Y. So here's X, and part of that is Y here. We have an I cell in X attached to Y. This is EI, and because of this relative group 0, we've got a homotopy that takes that to an I cell in Y. And we're going to denote this homotopy by capital Phi. So it goes from now the idea is to use this as an attaching map for an I plus 2 disk. But this was attached in the way we had before for an elementary expansion. So it's attached via an I plus 1 disk in its boundary. So this homotopy is the part I was calling F before, and we had, here's a di plus 2 attached via a di plus 1 in its boundary, where the boundary of that di plus 1 is in the I skeleton of X. And I'm going to call C is going to be the part of the boundary which is not F. So we've done an elementary expansion. We've still got this I cell which we didn't want in X. This is this intermediary thing, X prime. And now we collapse C. So what's going on here? We're thinking of C as an elementary expansion done on Y. So if we're just to let's view this from the top and ignore X for the moment. We've got Y, then we've got C, and the boundary of C is this part, which was our EI, and then there's the part in the boundary which is attached directly to Y. And the idea is to collapse C like this, and this then collapses this I cell EI to Y and gets rid of it. Now I'll do an example in a minute, the simplest example I can think of, so you can see what's going on. So what you're doing, this is the C is this dome part of the surface, and you're collapsing it over the top and into Y. And this is an elementary collapse. So then if G is this collapsing map from C union Y to Y, then X bar is just this collapse. It's X prime union G Y. So we're crushing C into Y. And so we've traded DI for an I plus 2 cell. Now this wasn't immediately clear what was going on to me when I was figuring this out, so an example should make this clearer. So Y is going to be D1, X is going to be D2, and Y is in the boundary of D2. So here's X, and let's see if I've got another colour. And then Y is this line around from the top to the bottom. And in X we've got this one cell which we don't want, and we've also got this 2 cell. I'm not going to label that at the moment. So we know that there's a homotopy from this one cell to this one. So this is the phi that I wrote before, just across the disk, dragging one side to the other, and we attach a 3 cell to this homotopy. I'm going to draw this in an instructive way. So here's Y going around on the left, here's E1 going around on the right. I'm going to push the disk up to be the northern hemisphere of a sphere, and this was X on the top, and we attach, there's a D3 in the interior of this sphere, and there's another, I'll call that E3, and then there's this lower hemisphere which is this E2. So we've just attached, cancelling 3 disk and 2 disk. So this is an elementary expansion, and this is X prime. Now what's C is this lower hemisphere, and we wish to collapse that. Collapse C. So just imagine this disk being collapsed round like that, and this takes this E1 all the way to Y, and we end up with a cell decomposition that looks like this. We have Y, and then we have a single 2 cell, which is C, which is attached, wrapping round Y like that. We have the single 2 cell, which was the original one we had in X. C's been crushed, and then the E3 is attached to the interior of this. So now the entire one skeleton is in Y, and then the rest is in X. clear? Okay, now we'll use this the cell trading lemma to prove that if the torsion is 0, that they have to be simple homotopy equivalents.
So that E1 then took sort of swept all the way underneath C and sort of crushed it into.
Yeah, so E1 has gone. E1's just rotated around, just like that, and has gone to Y, as C was crushed, sort of rotating around. So we want the right to left direction. Let's remind you what that was. If we have a CW pair, Y includes into X as a homotopy equivalence. This is a finite CW pair. Then the torsion being 0 implies that X is simple homotopy equivalent to Y, rel Y. So actually all these superfluous cells we had in X that weren't in Y can all be collapsed just to give Y without changing Y. So again, this is a somewhat sketch proof, but all the ideas should be there. So we know X is homotopy equivalent to Y, so we get that these relative homotopy groups are all 0. So we can apply this Whitehead cell trading lemma for any dimension. We trade all the cells in X minus Y of dimension less than or equal to the dimension of Y. We trade them up